Okay, so now that we have finished with our basic concepts, basic terminology, we want to move on to descriptive statistics and talk briefly about sort of the picture we paint when we talk about descriptive statistics, the picture we paint of the sample. Okay, so there are a few sort of descriptive statistics that I want you to be familiar with, that whenever we talk about descriptive statistics, these are what come to mind. And the first of these is the idea of frequency. When we talk about frequency, we're just talking about how often the various values occur. And there are generally four ways of us sort of elaborating or depicting the frequency. Two of these we use quite frequently. Two of these you may see but aren't used quite as much. Now, one of those is the stem and leaf plot. And I provided an example, a quick example of a stem and leaf plot. The reason we talk about frequency here, you sort of see this in a horizontal way. You kind of see how the data are laid out, and for the most part this sort of looks like a normal curve. If you were to take a line and draw it on the edges, it would look pretty normal. Okay, the reason they call it a stem and leaf is on the left side is the stem, which in this case are the tens place, and then on the right is the leaf, which again in this case are the ones place. So for instance, on that top line you see a 2 and then dot and then 333. Basically what that tells you is you have 3 scores that are 23. Okay, the next line you can tell that we have a 24, a 25, and a 25 in our data. The next line we'll see that we have 3 26s and 3 27s as a part of our data. And that's the stem and leaf plot. Not used very often, but again you might just want to be familiar with it. The second type of frequency chart that you will see, and this is the gold standard, you will see this a lot in research, is the idea of a histogram. It's similar to the stem and leaf plot, except that we sort of set this upright. It's now a vertical structure with the frequency on the x-axis or the y-axis and the value, if you will, on the x-axis. And so we kind of get a picture of what this data again looks like. What these data look like. Sorry, data are plural in case you haven't caught that from me already. So just forgive me if sometimes when speaking I refer to them in the singular sense, but data are plural. But we see our data here, and if you again were to track the edges of the bars there, you would sort of get this normal curve. And that's basically what a histogram gives you. The other thing you'll see very often is the frequency table. And here is an example of a frequency table. What we have on the left-hand column there are the actual values in the section marked frequency there. The little column to the right are the values, or the numbers of times the values occur. So the number of times a 1 occurs in our data is 3 times. The number of times a 2 occurs in our data is 1, and so on and so forth. Then you get percent and valid percent and cumulative percent. The thing I want you to be aware of is if you notice, percentages are different between percent and valid percent. Basically, the difference is under percent, if you go all the way to the bottom where you see the 5% and follow that out to the left, you'll see it says missing system. Basically, the percent column takes into account any data that you have that are missing. So in our particular case, we had one participant who didn't provide a score, so it's missing. Therefore, all of the percentages take into account that missing. If you look at the valid percent column, it does not count missing. So depending on which you want to report, generally speaking, we tend to report valid percentages within our research, but that's not always the case. You can kind of see what people report there. But that is the frequency table. The next thing you'll see, rarely, but you will see it, is this box plot. It's another way of describing or sharing the frequency of the data. You'll see the box in the middle is where most of the data occur. The line across the middle is the mean, and then those whiskers are sort of the extreme parts of the scores or the standard deviations of where the scores occur, with numbers out there for some of the more extreme scores. Okay, but that's box plot. You won't see it a lot, but just wanted you to be familiar with it. Okay, so beyond frequencies now for descriptive statistics, we also want to talk about the shape of our data. Okay, and this is very important. This is one of the things you will see a lot of in research and that you need to be focused on when you talk about your sample. With shape, First thing we want to talk about is the kurtosis. This is probably a new concept, new word to you, but basically it gives us a sense of how spread the data are, and we'll see this in a second as far as the shape. Okay, so we've got three different types of kurtoses. One of those is leptokurtic, the other is platykurtic and mesokurtic. When we talk about leptokurtic data, basically we are talking about data that are more peaked than we would expect from normal data. So if you think, this is at least how I remember it, leptokurtic is leaping, it leapt, so it's a little higher than we would have expected than normal. Okay, with platykurtic, on the other hand, it's lower than normal. The data are kind of squished. And sort of the imagery I use to help me remember platykurtic is sort of this idea of a plateau, or what I like is the idea of using a balloon. Imagine somebody stepping on a balloon, and the center of the balloon, it sort of takes the point and moves it out. And one of the other reasons I like the use of the balloon imagery is that if you step too much on the balloon in the middle, what happens? All the air puffs out to the shoulders. And that's really what we're talking about when we talk about platykurtic. Most of the data occurs further out than we would have expected. And then with mesokurtic, we're basically talking about a normal distribution. So if we had something sort of like this, okay, that would be a normal distribution. It's not too peaked in the middle, and it's not got too much of the data out in the shoulders. It's fairly normally distributed, and that's kurtosis. We're not going to spend a whole lot more time on it here, but I do want you to be familiar with this because you should be able to use these terms when describing your data. Okay, we can also talk about modality. And when we talk about modality, we're talking how often a value occurs, or what is the frequency of the most frequently occurring value. Okay, so for instance, we can have uniform. When we talk about uniform, we're saying that the data basically roughly occur with the same frequency. So if we go back to our example from before, if we were looking at, let's say, all ACT scores of students across the US, if we got a sample and it was uniform, let's say this occurs 3 times, okay, all of our scores, 18, 19, 20, 21, sorry, it should be a 1, and 22. We had 3 people in our sample get each of these scores. In other words, all the scores occurred with the same frequency. This would be considered a uniform distribution. And by the way, if we had this, we potentially have some issues with our stats that we run. So we don't want to have data that are equally distributed across all values. Okay, what we are looking for are normally distributed data. Okay. The other thing that we have here is the idea of a unimodal distribution, and that's basically where we have this peak. One value occurs more frequently than others. We could also have something that's bimodal, where instead of a single mode, we might have 2 modes. Okay? And quite often you won't see that the modes are exactly equal in height or frequency, but there's clearly 2 peaks here. That would be bimodal. And then we can also end up with multimodal, where you have more than 2 peaks. Basically at that point, whether it has 3, 4, whatever it is, we would call that multimodal. And it's just clearly more than 2 modes. Okay, and that covers modality. The last thing we want to cover on this particular set of descriptive statistics here with shape specifically is the idea of skewness. So we've covered kurtosis, we've covered modality, and now let's cover skewness in relation to shape. When we talk about skewness, I've stolen a line here from one of my professors years ago who said it's the tail that tells the tale. So if we had a distribution that looked like this, most of the data are clustered over here with the tail of the data this direction, which there are 2 general types of skewness that we have. We kind of have a positive skew and a negative skew, and since this is going to the left, or it's skewed left, we would consider this a negative skew. And the opposite would be true if it were skewed the other way. The majority of data are on this side, the tail goes to the right, so this would be a positive skew. So if I were to say, I collected my sample, I checked the descriptive statistics, specifically the shape, I have a leptokurtic, unimodal, negative skewed distribution, you should sort of be able to picture in your mind what shape that distribution might look like. Okay, and that's what we're trying to get at, because at some point you're going to have to use this to describe your data, all of which have implications that we'll talk about further when we get to the face-to-face section. Okay, so moving on with descriptive statistics, we have our measure of central tendency, which basically there are three central measures, or measures of central tendency. We have the mean, which is the basically mathematical average that you guys are familiar with, and please note in parentheses there that the little X bar, that references statistical notation for the sample mean, and then the mu, the little u there, is the Greek letter mu, which references the population mean. Okay, and then you also have median, and median is the number that occurs in the middle when the scores are arranged from lowest to highest, the number that comes in the middle. We tend to use median more often when there are extreme outliers or the data are skewed severely one direction. So you think about like median income levels. There are the Bill Gates and the Warren Buffetts of the world who severely skew average income. So to report average income wouldn't be completely reflective if we use the mean. So we often report the median income. It's the score that occurs in the middle. And then mode, as we mentioned before, is the most frequently occurring value. So one thing I want you to know, in a normal distribution, if this were normal, is that mean, median, and mode all occur at the same point. Okay, in a normal distribution, mean, median, and mode all occur at the same point. The final descriptive statistics, set of descriptive statistics that I want you to be familiar with relate to dispersion, or how the data are spread around the mean. We talk about sums of squares. You'll see this. Just know basically what I want to see is I've got a value here. How far is it from the mean? We're going to sum all of these up and we're going to get what we call the sums of squares. You don't have to be real familiar with this. I'm not going to necessarily test you on this, but here is the formula for it. Notice next is variance, which the shorthand for that is s squared, lowercase s squared for the sample variance. For population variance is omega squared. If you see either of these notations, you should be familiar with what that means then. And if you notice in the formula for variance, in the numerator, which for those of us who have been out of math for a while, it's the stuff on top of the line, the numerator, that is the formula for sums of squares. So if we were looking at variance, it's in essence sums of squares divided by n minus 1. Real quick test. What does lowercase n mean? It's the sample. In this case, sample size. Lowercase n is sample size. If I took a sample of 100 students, high school seniors, my sample size is 100. It would be 100 minus 1. So to get my variance, I would take sums of squares divided by 99, or the 100 minus 1, and that is variance. And then the last thing I want you to know, and this we will use all the time, is standard deviation. When we talk about standard deviation, we are talking about the average spread of our data around the mean. And what I want you to notice, from s squared to s, I can erase this. To get from s squared to s, basically all I'm doing is taking the square root of s squared. Okay, pretty simple, but you do need to know where this comes from, and this is how we get standard deviation. If you felt so inclined at some point to work on your math, you could calculate all this by hand, and if we were in a different program other than EdD, so be thankful you're in an EdD, I might have you do this by hand frequently so that you can kind of get used to seeing how this works. All I want you to know is just basically sums of squares, variance, and standard deviation are all related. Okay, there is a continuity between them. And then the other thing and final thing that I want you to be aware of with descriptive statistics is the idea of range. Okay, and we have two different types of range: observed and possible. So again, think about the ACT scores. What is the possible range of ACT scores? I think it's from 2 to 35. Those are the theoretically possible scores a person could get on the ACT. However, if we took a sample of high school students, our observed range would be the actual range of scores from our students. So let's say we took a sample of 100 students, and our lowest ACT score from our sample was 14, and our highest was 35, then our range is 14 to 35, our observed range. One of the reasons that this becomes important is for you to consider this idea of range restriction. Okay, so let's say in this sample of ACT students, you're looking to see if your program has an effect on ACT, and you take a sample of students, and let's say for some reason all 100 of your students scored between a 34 and a 35. Okay, they all got a 34 or 35 before the program. We have severe, what we call range restriction. We don't have the whole range represented here. It's just a certain part. Now the question we would have is, what good is our program going to do? In this case, our program is likely not to show any effect, but probably due to the idea of range restriction. And we'll talk more about that in the days to come.